G7A will be power supplies and schematic symbols. What safety feature does a power supply bleeder resistor provide? The bleeder resistor discharges the filter capacitors in the power supply. And here you can see a diagram. You have the rectifier, which changes the AC to DC. Here you have a filter capacitor, which can store quite a large amount of electricity. And here you have the output from it. Now, the bleeder resistor isn't necessary to make the thing work. That power supply will work just fine without that bleeder resistor. But if you disconnect the load from this and then you turn this off, that filter capacitor will continue to hold that voltage in there. So the purpose of the bleeder resistor is to bleed down that filter capacitor so that it won't have a high voltage in there. If you need to reach in and start working on something or something like that, it will bleed that off to where it won't shock you. Which of the following components are used in a power supply filter network? A power supply filter network, and we've seen this before, power supply filter network has capacitors and inductors. There's that filter choke again. Okay, and here are the electrolytic capacitors again. Remember, they have a very high capacitance for their physical size. And then once again, here is our bleeder resistor that bleeds the charge off of those capacitors. What's the peak inverse voltage across the rectifiers in a full wave bridge power supply? In a full wave bridge power supply, the peak inverse voltage is equal to the normal peak output voltage of the power supply. So if we had an output here of 100 volts DC, then the peak inverse voltage across the applied to the diodes would be 100 volts DC. What's the peak inverse voltage across the rectifier in a half-wave power supply? In a half-wave power supply, the peak inverse voltage is equal to 2 times the normal peak output voltage. So in this case, if we had an output voltage of 100 volts DC, the peak inverse voltage would be 200 volts DC against the back of the diode here trying to go the wrong direction. What portion of the AC cycle is converted to DC by a half-wave rectifier? Let's take a look at a drawing. Here's our AC. And if we look at the cycle, here's 0 degrees, here's 90 degrees, here's 180 degrees, here's 270 degrees, here's 360 degrees, which is the same thing as 0 degrees when we start the cycle all over again. Okay? So it's just like going around a wheel, 0, 90, 180, 270, 360. Okay, and then we've said previously that this diode will pass only the positive side of that AC wave, so that we are converting only 180 degrees of the 360 degrees of that cycle using a half-wave rectifier. So here's 180 degrees, here's 180 degrees, here's 180 degrees here. What portion of the AC cycle is converted to DC by a full wave rectifier? A full wave rectifier, if you look at this drawing here, you see a diode that is conducting in this direction. And here they put the load resistance right in here so it looks like it's part of the circuit, but that's actually the load. So on half a cycle, this diode conducts. On the other half of the cycle, this diode conducts. Okay? And the reason that happens is this is the common point on the transformer. This is a center tap transformer. This is the common point. And so you get conduction through this one for half the cycle. You get conduction through this one for half the cycle. And you end up with a waveform that looks like this, which is full wave rectification. Okay? So what portion of the AC cycle now is converted to DC? The whole cycle, 360 degrees, is converted by the full wave rectifier. What's the output waveform of an unfiltered full wave rectifier connected to a resistive load? And we have just seen that, actually. It's a series of DC pulses at twice the frequency of the AC input. So if this is 60 hertz, here we have a 60th of a second from here to here. Okay, another 60th of a second from here to here. Okay, after putting it through the rectifier, we still have a 60th of a second from here to here, but now we have two pulses in it, don't we? So we have a series of pulses at twice the frequency of the AC input. A series of DC pulses at twice the frequency of the AC input from a full wave rectifier. Which of the following is an advantage of a switching mode power supply as compared to a linear power supply? Okay. The switching mode power supply operates at a much higher frequency. The linear power supply just takes the frequency that comes to it out of the wall, the 60 hertz. And the higher frequency operation allows the use of smaller components, which can be an advantage. In a switching mode power supply, it's typically operating at about 20,000 hertz instead of the 60 hertz for the analog power supply. Okay? To give you an example of an advantage in size and weight, an analog supply that supplies 20 amps, this is a common brand called Astron. The case is 5 by 9 by 10.5 inches, and the whole thing weighs about 18 pounds. Okay? On the switching type power supply, also from Astron, a 25 amp supply measures 3 by 7 by 9 3/4 inches, weighs only about 5 pounds. And I can tell you that since I've moved to Hawaii, I'm buying switching power supplies rather than analog power supplies because they're a lot cheaper to ship. Okay, we're in the diagram now. If you've printed out the diagram, you can follow along on there, or I have it on the screen for you. Which symbol in figure G7-1 represents a field effect transistor? Okay, we have two transistors here. We have a transistor there. We have a transistor here. And the one that's the field effect transistor is the one that has this heavy straight bar with the arrow coming in here at the gate. Okay, so symbol 1 is the correct answer for the field effect transistor. Which symbol in figure G7-1 represents a Zener diode? We have 3 diodes represented. There is one here. It looks like it has a capacitor on its nose there, doesn't it? Okay. And then this looks pretty much like an ordinary diode. And then here's one that's got this thing that looks like a Z, perhaps, on it. And this is the Zener diode. Okay. And the Z here, that Z-shaped line, is your tip-off for the Zener diode. So symbol number 5 is the Zener diode. This is called a varactor diode, and this is used, this has a variable capacitance depending on what the voltage applied to it, the DC voltage applied, and this can be used as a tuned circuit, or in a tuned circuit to control frequency. And that's why it shows it as a capacitance there. Okay, but the Zener diode has the Z-shaped anode, and it is symbol 5. Which symbol in figure 7-1 represents an NPN junction transistor? Here's the other transistor, and it is an NPN junction transistor. So symbol 2 is the correct answer. Which symbol in figure G7-1 represents a multiple winding transformer? Okay, winding is going to tell you have coils, right? And here you have coils, and here you have a coil, okay? And the one with multiple windings is this transformer right here, isn't it? Where we see the winding, and we see the iron core, and we see the other winding, okay? So this is the multiple winding transformer, symbol 6. Okay, which symbol in figure G7-1 represents a tapped inductor? Our other inductor here has a tap, so it's a tapped inductor. Correct answer for that is symbol 7, the tapped inductor.